In this session, we're going to look at operating system services. We're going to look at interfaces, and we'll talk a little bit more about system calls. So first off, we'll look at the services provided by an operating system and how system calls are used to actually provide those services. And then we'll be able to identify the strategies, some of the strategies for designing an operating system. And then lastly, a little bit more detail about system calls. So operating system services. So an operating system makes services available to programs and to the users of those programs. And these may differ from operating system to operating system, but there are some common classes. So in this diagram here, you can see at the top here, we have user and other system programs. In the middle, we have operating system and all the services that it provides. So you can see there's a lot of services. And then below, access to the actual hardware. So let's take a look at some of these services. So first off, here we have the user interface. So it's commonly some sort of GUI. Usually there's a complementary CLI or command line interface, like terminal for Mac, command prompt for Windows, and bash shell for Linux. But we also have graphical user interfaces, which are most commonly used by your standard user. Here we have program execution, which loads programs into memory, and it provides a way to track normal and abnormal execution and can act accordingly. We also have input-output operations. So the operating system provides a mechanism for handling input and output. Here we have file systems, so the ability to read and write files, to read and write to directories, to create directories, and also different levels of ownership. So we can apply permissions, for example, to files based on requirements. Here we have communication. So inter-process communication, the two main concepts of message passing and shared memory are two ways to handle communication between processes. We'll talk in a bunch more detail about this in future sessions a few weeks down the road here. Then also another one I want to look at here is error detection. So this may occur in the CPU, memory hardware. The operating system must take appropriate action. So give an error code and or terminate the process. So some way of handling the error in hopefully a graceful way. Okay, moving on. Oh yeah, so here's just what I was saying in a nutshell. So the user interface is commonly some sort of GUI. Mouse, touchscreen these days, touchscreen on smartphones, and also some laptop devices allow for that touchscreen, Chromebook, for example. Program execution, so it loads programs into memory, ways to track whether a process or program executed normally or there was some sort of an abnormal execution, so handling errors. Input-output operations, pretty standard for an operating system, has to handle access to and from devices like hard drives, for example. File systems, so reading and writing files, creating directories, giving levels of ownership, so again, based on permissions. And then communication, so again, message passing and shared memory are the two main, what we call IPC, or inter-process communication methods. Then error detection may occur in the CPU, may occur in memory hardware. The operating system must take appropriate action. So some sort of an error code, and hopefully terminating a process so that it's not blocking access to any resources. Then resource allocation, depending on which resources are requesting or which applications are requesting access to resources, to multiple processes. For example, scheduling routines for the CPU, right? Like we must have a way of being able to give multiple applications access to execute using the CPU, and then also peripheral devices, so handling interrupts. And then logging is a way to keep track of program usage for CPU and memory. So we can look at that sort of usage through tools like Activity Monitor or in Mac, or Resource Manager in Windows. And then protection and security, so ensure processes don't interfere with each other, and then controlling internal and external access to resources. So these are all things that an operating system should provide. Looking at the user and operating system interface, so like I was talking about, just to go in a little bit more detail, the difference between a CLI and what a CLI is versus a GUI. So command interpreters are basically just ways to allow you to type in commands. So the main function is to get and execute the next specified command. So you go to a tool like Terminal in Mac, or you go to a tool like Command Prompt in Windows, and you type in the command that you would like to execute. So create, when you want to create something, you may want to delete something, list, right? Like look at ls for list directory to show the contents of a directory. You may want to print something, copy. A lot of times we'll go there to execute code, maybe to compile a C program, for example, and then run that C program. Lots of different reasons why we would use a CLI. And then the graphical user interface is the mouse-based and menu-based system. So a desktop metaphor, traditionally on a desktop or laptop. So a Mac GUI or a Windows GUI, or even these days a Linux GUI, right? So it allows us to basically point and click, or if we're using a touch screen, being able to touch on an application to open it, as an example. So these GUIs first appeared in the 1970s, but didn't come into real kind of prominent usage until a little bit later in the 1980s with Mac, and then followed soon after by Windows. So like I mentioned before, when I was in school, in my undergrad computer science, getting my degree, I learned how to program Windows applications because at that time, Windows was transitioning into Windows 3.11, which was kind of its first mainstream GUI interface that became very, very popular. These days, though, this is what you're probably most used to seeing. If you have a Apple iPhone, or the Android GUI is not much different, right? We still see each application as an icon, whether it be a system application or whether it be a user application. So more recently, touchscreen and app interfaces have been popularized. So each of the icons on the right there represents some sort of an application. Again, whether it be a system application or a user application, of course, depends on its purpose. So iPhone and the iOS are considered to be the most influential innovations in this century. So almost 25 years in, I don't think too many people would argue that this has probably been the biggest change in the way that people access and use technology. So the command line interface and the GUI, traditional GUI, have been replaced by the swiping functionality and the simulated keyboard. Being that I'm old school keyboard and I can type quite quickly, I find any kind of productivity on these type of devices, I find it frustrating. But for those of you who are kind of native iPhone and Android users, you probably can, well, I know you can navigate this as a productivity tool much better than I can. Okay, a little bit more on system calls. So system calls provide an interface to operating system services. They're generally available as functions written in C. And this is what we're going to look at quite a bit in this course, is how do we write code to perform system calls in Linux, as an example. So low-level tasks, even lower-level tasks, may be written in an assembly language. So I actually, back in the day when I was doing my undergrad, again, in the 90s, we did a whole course on assembly language. So back then, memory was still very expensive relative to how much memory you could get. So less bang for your buck, so to speak. And so optimizing memory by using assembly language was a very in-demand skill. So even simple programs require many system calls, right? Like you're always typing, you're always swiping, you're always saving, right? These days, particularly with autosave. So even if you're using a very simple program, it will still make a multitude of system calls. And typically coders design programs using what are called APIs. So the operating system itself, so whether it be Windows or whether it be Linux as an example, provides these APIs that simplify accessing system resources. So they're pre-written functions, provide access on behalf of the programmer. So you don't have to write the code in assembly language. It's already been written for you and is provided to you in a library, an API library, as an API. So all you need to do to know, for example, to read in Linux is you need to know that you need to call the read function. Okay, and then that function will go ahead and perform the tasks for read. And now system calls occur in different ways depending on the computer in use. The amount and type of information required depends, of course, on the operating system. So we'll look at Windows calls versus Linux calls in a second. You can do the same type of task, but how it performs that task may be different. So for example, to get input, we may need to specify the file to use as the source and the address and length of the memory buffer in which the file should be read to. So that requires quite a bit of knowledge about memory and such, and quite a bit of detail. So three general methods are used to pass parameters to the operating system. So we pass them in registers. We store the parameters in a block. So remember we talked about blocks of memory and how we can manage which ones are available through bits, for example. And the third one is we can push them onto a stack by the program, or we can pop them off the stack by the operating system. Okay, so remember we talked about stack as a particular data type where it's last in, first out, so like a stack of dinner plates. Now some OSs prefer the block stack method because it does not limit the number or the length of parameters passed. So again, slight differences between operating systems on how the actual execution occurs. Now there's 6 types of system calls. So just to go through them, there's the process control. So create, load, execute, terminate. File management, right? So these are pretty standard. Create, delete, open, close, read, write, etc. Device management. So request access, release, attach to a device, detach. Information maintenance. So transferring information, debugging programs. Communication, so message passing model, the message passing model versus the shared memory model. We're going to talk in great detail about this soon. And then lastly, protection. So controlling access to resources provided by a computer system. So for example, permissions. So depending on the type of person accessing, we allocate permissions accordingly. And then lastly, I just wanted to show you what I meant by different APIs provide different ways in which we call a function that performs the same task. So if I'm talking about process control, you can see in Windows we use the create process, and in Linux, Unix, we use the fork command. File management, to create a file, we say create file. In Unix, it's open. Right? So this is very C-ish in that we use short, concise function call names. Read file, read, write file, write. You get the idea. Things like setting a timer. We use set timer in Windows, alarm in Unix, Linux. Communications, create a pipe or pipe. Protection, set file, security, or chmod. Right. So with chmod, we just set or reset bits that on a file or on a directory or on a resource that give certain levels of users access and deny certain level of users access. Okay, so you can see that we can do the same things, right? It's just if we're programming it for Windows, the function calls the API, right? Because all of these functions are contained in APIs as an API, right? The Windows API is different than the Unix API. But generally, you can do the same sort of things. So that's what I want to show here. All right. Right, so that's all I wanted to talk about in this session. So just to recap, we looked at services provided by an operating system, looked at how system calls are used to provide those services. We looked at identifying the strategies for designing an operating system. And then lastly, we went into some detail about system calls. And we looked at, in the last slide, the Windows API versus the Unix API in regards to how we call particular functions to perform different system tasks. All right, thanks for tuning in. We'll see you in the next session.